In this segment, I'm going to talk about vector analysis, and by that I mean the mean electrical axis of the heart. In this animation, and I've got it running very slowly so we can observe the events. At the top is the animation of the electrical dispersion. Down here I'm looking at the electrocardiogram. The little green ball is telling you where we are on the electrical cardiogram relative to this event. So if we start this thing, at the SA node, we see it firing. The electrical wave moves around the atrium, down through the AV node, down the bundle of His, and then spreads around the ventricles, and stays contracted until this point when we see the repolarization, which is the T wave of the electrocardiogram. Okay, one more time. SA node, atrium, P wave, QRS here. All myocytes are contracted. Now they begin to relax, T wave. So when I talk about the mean electrical axis, one of the things that you'll notice is that this wave of activity moves downward, to the right, to the left, upward. It moves in all directions, but the average movement is going to be from the AV node down toward the apex. In a normal individual, the average mean electrical axis is going to be somewhere around 60 degrees. In addition to the electrical activity moving down initially through the septum and then down and around, left, right, etc., all the way down to the apex, the vectors also move from the endocardium to the epicardium. In this case, I'm showing the electrical activity beginning in the endocardium and moving toward the epicardium, and this happens both on the left and the right side, and I'll draw a few more in here. One of the things you'll notice is that these vectors, because of the larger muscle, these vectors are bigger than these vectors, and therefore the left side tends to overwhelm the right side, giving us a leftward shift to the vector. As we move up, we see the vectors continuing to move on and begin even turning in an upward direction. Now we can see the mean axis, the mean vector, pointing here, which is partly the contribution of the activity moving down the septum and then around the ventricles, and partly because we're beginning to see now the vectors forming from endo to epicardium. The opposite happens during repolarization. Here we can see we're repolarizing from the epicardium down to the endocardium, and this is happening on both sides, and again we see this happening. We also now see the vector pointing in this direction, partly because the apex of the heart begins to repolarize before the base, the basal regions, and partly there's the contribution of epi to endocardium. So let's look at this. I've got 3 cells here, and I have my negative or reference electrode on this cell here on the left, and the positive or signal electrode over here on the right. I'm looking at a depolarizing wave and a repolarizing wave. The red arrow is the depolarizer, so I trigger this cell to depolarize, and the wave moves from cell to cell toward the positive electrode. I see an upward deflection. I like to call it a positive deflection to help me recognize that it's moving toward the positive electrode. If this same cell repolarizes first, the repolarizing wave will move toward the positive electrode, and since repolarization is the opposite of depolarization, I see a downward or negatively deflecting wave. So this could be our R wave, this could be our T wave. In this example, the cell on the right depolarizes first. The activity moves toward the negative electrode. We see a downward deflection. If that same cell repolarizes and it moves in that direction, we see the opposite, an upward deflection. Here in this example, we are depolarizing this cell in the middle. The wave of depolarization will arrive at each electrode simultaneously, and we'll see a small blip, but no discernible upward or downward deflection. If that same cell repolarizes first, and that wave moves in both directions, we will see no significant waveform. But that's not how the system works. In the heart, the cells nearest the negative electrode depolarize first, and the cells nearest the positive electrode repolarize first. Depends on your electrode placement. So if this cell depolarizes, the wave will move toward the positive electrode. We see an upward R wave. Now the cell on this end begins repolarizing first, and it moves toward the negative electrode. Since repolarization is the opposite of depolarization, but the wave is also moving in the opposite direction, we now have a double negative, so we see an upward deflection. This could be the AV node, this could be the apex of the heart. And in a normal heart, this is the direction of depolarization and repolarization. The T wave may be inverted following a myocardial infarction. It may also be inverted with potassium imbalances, or the limb lead, for example, AVR, normally shows an inverted T wave simply because of the direction of the placement of the electrodes. In this figure here, I'm showing the Einthoven triangle, which is made up from 3 limb leads. Lead 1, the negative electrode, is placed on the right arm and the positive electrode on the left arm. Lead 2 shows the negative electrode on the right arm, the positive electrode on the abdomen. Lead 3, the negative electrode on the left arm and the positive electrode again on the abdomen. We normally place electrodes around the chest. However, in this example, you can actually use these limb leads, the right arm, and left leg. So any voltage moving from the right arm to the left arm is going to move along that limb of the triangle. Any voltage that moves from the right arm to the left leg is going to have to move along in this direction, and the left arm to the left leg, the same thing. We could use the right leg, but by convention, people pick the left leg as the standard. Now, if we look at these 3 electrocardiograms, and I'm just showing the R waves, for these 3 different limbs, we see lead 1 has an upward lead deflecting but relatively short R wave. Lead 2 has an upwardly deflecting but taller R wave. Lead 3 has an upwardly deflecting and short R wave. So if we take that triangle and just draw arrows, here I'm going to be drawing an arrow pointing toward the positive electrode representing lead 1 because it is upwardly deflecting. The arrow is going to point toward the positive electrode, and I center that on the triangle and make it a relatively short arrow. And let's go to lead 3 because that's the same size. It's also upwardly deflecting or positive direction. And so I draw an arrow the same size as lead 1 pointing toward the positive electrode. Lead 2 has a taller wave, also positive direction. I draw an arrow pointing toward the positive electrode, but about twice the length of the other 2 arrows. Connect all the tails, connect all the heads, and then draw a single arrow moving from tail to head. That is my mean electrical axis of the heart, and that turns out to be 60 degrees. That is represented here as an average normal electrical axis of the heart. In this example, I have a short downward or negatively deflecting R wave, so I will draw a short arrow pointing toward the negative electrode. Here on lead 2, I have a short upwardly deflecting, and I'll draw an arrow in that direction. Lead 3 is taller and upwardly deflecting, so I will draw a longer arrow along lead 3 pointing toward the positive electrode. Connect all the tails, connect all the heads, and then draw one arrow from tails to heads, and now I have 120 degrees right axis shift. It's shifted toward the right. And in this one, I will leave this one for you to examine. We have a tall lead 1, upwardly deflecting, a shorter lead 2, upwardly deflecting, and a short lead 3, downwardly deflecting. Cardiologists use several other leads. The augmented voltage lead, labeled AVR, AVL, and AVF for right, left, and foot, gives us 3 more angles. So now we have 6 angles to get an image of the frontal plane of the electrical activity of the heart. Another placement of electrodes are called precordial leads, and here we see V1 through V6, looking down through a transverse section, V1 through V6. V1 and V2 are on either side of the sternum, and we move around to V6, which is placed under the left arm. And this gives us a front-to-back or dorsoventral image of the electrical activity. Well, the augmented leads and the precordial leads we'll save for another time. Moving back to the 3-lead Einthoven triangle, I'm just going to pull one of those leads out, and that's lead 2, negative, positive. And we're looking now at a mean electrical axis, which is in parallel with the side of the triangle representing lead 2. We see a very tall upwardly deflection because the arrow is pointing toward the positive electrode. Here I'm moving it leftward. This is a left shift. It's also, the arrow is pointing more toward the positive than the negative electrode, but since it's not parallel, we're seeing a shorter R wave. And this one right in here, it's now perpendicular to that side of the triangle representing lead 2, and we see no discernible deflection. There's a slight upward, downward, but there's no way to determine whether this is up or down because it's perpendicular. It's moving both toward the negative and the positive equally. In the next one, we have the arrow now pointing up. We're still moving to the left. but the tip of the arrow is pointing more toward the negative than the positive electrode. And it's obliquely set to the side of the triangle representing lead 2, so we see a downward deflection but shorter R wave. In this last one, we're back again parallel to that side of the triangle, but in this case, the arrow is pointing toward the negative electrode. Because it's parallel, we see a tall R wave, but it's pointing downward or in negative direction. There's not much you can get from just a single lead. In this one here, of course, we can tell that it's an isoelectric lead because it's perpendicular, but we don't know whether it's pointing in this direction or if it's pointing in the opposite direction. You really need all three leads to get a handle on the direction of the mean axis. Let's look at this. This is a real electrocardiogram. We're seeing lead 1, lead 2, lead 3 over here, AVR, AVL, AVF, and V1 through V6. So focusing on just the three-lead Einthoven triangle, we have lead 1 upwardly deflecting, shorter than lead 3, lead 2 downwardly deflecting, and about the same size as lead 1, possibly, arguably a teeny bit taller, and lead 3 being the tallest one, but also downwardly deflecting. So let's start by drawing our short arrow pointing toward the positive electrode for lead 1. And I'm drawing these perpendicular lines because we're going to use those to connect later. Lead 2, approximately the same size, but pointing downward or negatively, so I will draw a similarly sized arrow pointing toward the negative electrode. Lead 3, also downwardly deflecting, but taller, and so I will draw an arrow pointing toward the negative electrode. Now I'm going to connect all the tails and all the heads, and I have this. So we're pointing upward, approximately parallel to lead 3. Using this protractor, I can see that the angle is approximately minus 60 degrees. The arrow is pointing toward the minus 60. This electrocardiogram was also analyzed by a computer, and the computer estimated the mean electrical axis as minus 62. This is not a bad approximation. Once again, I want to just point out that AVR up here, we see the T wave here, here, negatively deflecting. This particular electrode is positioned such that the T wave normally points negative. At this point, I want to move on and use my vector simulation to analyze a few different angles and see what the R waves will look like. In this simulation, I have placed a protractor inside the Einthoven triangle, and I'm looking at the R waves here, lead 1, lead 2, and lead 3. I'm going to move this from the normal 60 degree and start to move it around. And as you can see, the waves change shape. I'm now perpendicular to lead 3, so lead 3 shows 0 deflection. I continue moving it around. I'm now parallel with lead 1. Lead 1 has the largest deflection. Continue moving it around. And here we see minus 60, which is the mean axis that we saw in the PowerPoint presentation. Cardiologists consider the normal mean electrical axis to occur when neither lead 1 nor lead 2 has a downwardly deflecting R wave. In this case, I'm looking at 90. Lead 1 does not have a downwardly deflecting, nor does lead 2. And if I move this around, see lead 1 and lead 2 are both upwardly deflecting. And finally, at minus 30, neither of them are downwardly deflecting. If I continue moving, we're beginning to see lead 2 start to point down. This then is considered abnormal. So from about 90 degrees to minus 30 degrees, that range is considered normal. If we move to minus 60, which is what we saw before, lead 2 is downwardly deflecting. If we move around here to 120 degrees, we see lead 1 is downwardly deflecting. In fact, anywhere throughout here, one of the leads, or both, will have a downward deflection. Until finally we're back to minus 30 degrees. Neither are downwardly deflecting. If one of the leads is the isoelectric lead and shows no deflection, the other two leads must be of equal size, either pointing up or pointing down, must be of equal size. So we know it's perpendicular to lead 2, but we don't know which way. Is it moving in this direction, or is it moving in the other direction? Well, we just simply need to look at one of the other two leads. We see that lead 1 shows a upward deflection, so the axis must be pointing toward the positive lead. The other thing you can tell fairly quickly by inspection is when two of the leads are the same size and the third lead is bigger. So in this case, leads 1 and lead 3 have an upward deflection, but they're of equal size. Lead 2 is the longest one, so we know that our mean electrical axis is in parallel with lead 2. Is it moving toward the positive or toward the negative electrode? All we need to do is to look at lead 2 and we can see that it is upwardly deflecting and therefore it's moving toward the positive electrode. If we are somewhere in between, this becomes a little more difficult to estimate by observation. And this is where the augmented voltage leads, AVR, AVL, and AVF, come in handy. But you could probably make a fairly good approximation. Since lead 2 is nearly 0, it's almost perpendicular to lead 2. Lead 3 is a little bit bigger than lead 1, so you know that we're somewhere between minus 30 and minus 60. In this case, it's minus 40. That then concludes the talk on the mean electrical axis of the heart and vector cardiography.